Here, could you put this in your pocket? Oh, sure. Just put that in your pocket and then to your shirt. Like this.
Yeah, so it's this term right here that throws me off. I'm not sure how to use it. Try to get rid of it.
All right.
So it's just the RMS of this. So the RMS part's not the issue. It's this term right here. I'm not sure how to get rid of it.
So the question is about the calculation of the RMS value of a sine wave. As we know, the RMS value indeed involves taking the integral of the squared version of the signal. So 1 over the period of the signal times the integral of that function over a single period. And then we've got a squared sine of 2 pi f naught t plus phi squared dt. First, we have to use one of the identities, trigonometric identities, that converts a sine squared into double the angle, the sine of 2 alpha or whatever you call it. This is named alpha, right? Then
Oh, is it the 1 over 2 and then it's like cos alpha plus beta minus cos alpha minus or plus?
it can be written in terms of the sine of twice the angle. I can't exactly remember what that was, but it's going to be a square right here. Then we've got 1 over 2, the best of my knowledge, 1 minus
Oh, yes, that one, yeah.
sine of 2 times 2 pi f naught t plus phi.
Yeah, so this is the step that I was talking about. I'm not sure what to do with this. Like, here. I think it's cosine, but it's not right.
Is it cosine? Cosine.
It's close. It's fine, yeah, it's 1 minus.
All right. So, any idea how to proceed forward from this point?
It's also a 2, so it's a squared over 2t. The whole thing's 1. Oh, you still inside it.
Let's go. So the problem is with this constant phase, which is not a function of time as it has to be. So what do you think we have to do with this? We're going to take the integral of a cosine function. If that constant angle phi would be 0, then the cosine function would start from its peak value at t equals 0, right? So this is the situation with phi equals 0. Now if phi is a non-zero constant, we have something like this, right? we're expected to do here is to calculate the integral of a cosine function over a certain period, which is, in this case, 2 cycles of the signal. So once again, this is the cosine function. And we are to calculate the integral over a single period of the signal. For instance, either a single period or 2 periods. Now, just for simplicity, assume that we are to take the integral of 1 cycle. Does it matter if I start from t equals 0 and end up with a, for instance, certain period for the signal, whatever it is? Or it would be okay if I start from one peak and go to the next peak. This is also the same sign. So the time shift or the phase shift, if it is constant, it doesn't change the area under the curve over a single cycle. So it's either this or this one. So exactly the same amount of area that you're leaving behind if you start from a different time, it's going to be added on the other side up to the area you're going to calculate. Is it clear?
We need to ignore that.
Just ignore that, because the period of the cosine function is the same no matter if phi is 0, negative, positive, whatever. So long as phi is positive. Exactly in the same way as you would, for instance, calculate the integral from 1, 0 crossing to the other one, or from one value of the sine of the cosine wave to the next one, or from one peak to the next one, right? It doesn't matter. These are all time shifts or phase shifts. They do not affect the area. Other questions? Was that clear?
I have a question. How did you get to decide where everything goes?
Well, there's a trigonometric identity. I can't remember exactly. Well, I wrote it here, but sine squared of alpha is 1 over 2, 1 minus cosine of 2 alpha. Please verify this if you have the identity sheet with you, but it's something like this. Please don't make notes of this unless you make sure that it is.
If that's not the it's a longer version. I know the longer version. I don't need to tell you about it.
Just please double check.
But that's fine.
Other questions?
So you gave another question. So you gave a transfer function like this.
Mhm.
You said this is the input.
Right.
This right here. Well, if you gave us this is the input, we can take the f of t of that, of the Fourier transform of that. My question is, would you want us to do you want us to do a bunch of mathematical stuff to simplify this? Because this is the transfer function, this is the input, so we multiply them with the output. So do you want us to do like the math cluster, like the complete nest converted back to time domain? And if so, could you give us a really basic one in the midterm so we have to scratch your head for half an hour?
Oh. The question is about one of the problems in the second set of sample problems, the one that was typeset, this one. Sample problems, number 2. There are 4 parts, A, B, C, D. I hope you still remember the basic concept behind the Bode plot. It's either omega or f, doesn't matter. Number 2 of problems, series 2. It says transfer function of a filter is given as h of f equals 1/1 plus JF over 10 kilohertz. So we are asked to find the output, the response to a given input. In the analysis of systems, when we have a transfer function h of f or h of omega, we know that omega is 2 pi f. Doesn't matter. When we're given a transfer function, in general, that transfer function is a complex function. So it has a real part and an imaginary part. Or in a different description, it has a magnitude and it has a phase. Since the transfer function is a function of frequency, then in general, both the magnitude and the phase would be functions of frequency. So we can draw those 2 parts of transfer function, I mean magnitude and the phase, versus frequency. For instance, something like this, whatever. What does this mean? It means that for a given frequency, for instance, omega 1 or f1, whatever, 2 pi f1, the transfer function has a certain magnitude and a certain phase. So let's name it, for instance, A1 and phi 1. Right. So if the input to the filter, to the system, is a single tone input, a single frequency input, if it is a sine wave or cosine, let's say x of t, let's assume that it is 1 millivolt sine of 2 pi 10 kilohertz t, for instance, right? This is part B of the same question. So if the input is a single frequency signal, means that exactly at the frequency of the signal, the transfer function exhibits a certain magnitude and a certain phase. These are the two effects of the transfer function on the signal when it goes through the system. So the pretty easy way of, and also, professional way of doing the math for the calculation of the output is the output in the time domain would be the same as the input in wave shape, so a sine function. Since the system is linear, it is the pre-assumption for all the systems we study in this course, then the frequency of the output would be the same as that of the input. The effect of the transfer function on the amplitude of the signal would be multiplication by the magnitude of the transfer function at that frequency, that is a 1. So we've got, for instance, A1 times 1 millivolt. And the other effect of the transfer function is to introduce some delay, which is equal to phi 1. And that is constant in time. It is a function of the frequency of the signal. So the easy way of finding the output would be, for this case, for the case where the input is a single frequency one, is just to calculate how much the magnitude and the phase of the transfer function is, and then multiply the input amplitude by the magnitude of the transfer function, and add up some constant phase, which you can calculate at the frequency of the signal from the transfer function. So that phase is going to be added up to the 2 pi f naught t. This is the easiest way to do it. And that is based on some basic knowledge that we have. But if you want to do the math based on just Fourier transform, that would be also possible.
Could you upload the solutions to the second set of questions online?
Sure.
Then we start answering. We have a question.
Oh, you don't have the question?
We have the question. We don't.
You
have
do?
the
Oh, you don't have this. But the standard way of finding the output for instance, for 2D, x of t is 1 millivolt, sine 2 pi 10 kt is to find Fourier transform of your signal first. X of f equals 1 over 2j times delta function of f minus f naught, which is now 10k delta of f plus 10k. Now this 1 is indeed 1 millivolt. This comes from Fourier pairs tables that are available to everyone. So this is x of f. We've got h of f which is 1 over 1 plus jf over 10k. And we know that y equals the product of the input and the transfer function. So what happens if I multiply a function with a delta function?
That function is shifted to the function, so in this case 10k. So that function will be shifted to 10k. And then that's fine.
Suppose that I've got a function in frequency.
So it's not shifted, sorry, so that function is value has.
Yes. So if I multiply that function with a delta function with a certain amplitude, we know that the delta function is 0 everywhere, but at f naught. So the result would be zero everywhere, but at f naught. And that's going to be a delta function at f naught with the amplitude of a times b. Right? This is what we already talked about in the class. And it makes every sense. See, you are to multiply the two functions at all the frequencies, and the only place where the product would be non-zero is at f naught. So now the product of xf and h of f would be indeed calculated based on the multiplication of delta function and the transfer function. So the product of the first term and h of f would be how much?
You just substitute f equals 10k.
Yes.
You just find out.
So let's have f equals 10k. That will be cancelled out with the denominator, and the result would be a term of 1 over 1 plus j times a delta function at the same place, right? This is the first term. And the second term would be so 1 over 1 minus j times the same delta function, delta of f minus 10k.
Wouldn't one be plus and one be minus?
Which one?
So the two delta functions, wouldn't one be plus 10k minus 10k?
So where's this delta function located? At
F equals 10k.
f equals 10k. So let's replace f in h of f by 10k.
And so wouldn't that be plus 10k? Delta of f plus 10?
This one?
The second.
The second one, yes. No, this one would be located at f equals negative 10k.
But that's how you got the second term there, didn't you? 1 over 1 minus j?
That is because Now you're calculating this function, h of f, for f equals minus 10k.
Wouldn't the second delta function?
Oh, sorry. Sorry, that was unintentional. Yeah. So now what we've got is this function for the output in the frequency domain. So what do we do now? Do you remember what is 1 over 1 plus j? How do we calculate this? Let's multiply the numerator and the denominator by 1 minus j. 1 minus j over 1 plus j times 1 minus j. Childhood memories. So many years back. So what is 1 plus a times 1 minus a? Do you remember the identity? A plus b times a minus b. A squared minus b squared. So 1 plus j times 1 minus j. What is the result? 1 minus j squared. What is j? Do you remember? Square root of negative 1. When it is squared, then I'm going to get 1 minus minus 1. It's 2. Right. So 1 over 1 plus j will consequently be 1 minus j over 2. In the same way, 1 over 1 minus j would be 1 plus j over 2. Why do I do this? What is the purpose of converting 1 over a term to simply just one simple number? That is to more simply work with these two terms. Now, this is just a reminder of what you're expected to know about complex numbers. So y of f would be 1 over 1 millivolt over 4j times 1 minus j delta of f minus 10k minus 1 plus j times delta of f plus 10k. Now, what we've got is 1 over 4j times delta of f minus 10k minus delta of f plus 10k. Does it resemble anything to you?
Oh,
Sign? Yes. Taking into account 1 over j as... Okay. Now, what remains is minus j times delta of f minus 10k, what, plus, yes, plus delta of f plus 10k. This is the essential term for a cosine. to write 1 over 2 outside this bracket, and then sine of 2 pi 10 kilohertz t minus cosine of 2 pi 10 kilohertz t. What is a cosine? Fourier transform. It is 1 over 2 times delta of f minus f naught plus delta of f plus f naught. Sorry to bother you with something you tried to forget, but now in this course we do need those Fourier transform pairs. Now the only thing that remains is to make this expression a little more straightforward. And that's going to be one millivolt over square root of 2 sine of 2 pi 10k minus pi over
why can't you just leave it like that? Why are we going to the extent of doing that whole thing?
Pardon?
Why don't we just leave it at the step above? Why are we going to this last step?
This is fine. This is fine. But I just wanted, the end result to be in a form that you could compare it with this form, right? So this is the same explanation in terms of the magnitude and the phase. The easy way to come up with an expression for the output. So the output would be the input times the magnitude of the transfer function at that frequency times sine function of the same frequency term, 2 pi 10k t, plus a certain angle. And what is that angle? That is shown. Question? Here. Suppose that this is x1 of t, constant phi. And this is a unit impulse, delta function at, let's say, 1. This is x2 of t equals 1 times delta of t minus 1. We are to find y equals x1 times x2. So let's find the result by multiplying the two functions point by point. right? So the result would be 0 and 0 everywhere, but for t equals 1. What do we have at t equals 1? We have an impulse. So 1 times the value of x1 is 5. This would be 5 times 1 times delta t minus t1 minus 1. Right? Now, let's now consider x3 of t. x3 of t, which is, for instance, 1 plus 2t. Just a given function. Now the product of x2 times x3 is again 0 everywhere, but at t equals 1, and at t equals 1, x3 would be, for instance, how much? Let's say 2, 3, no, whatever. It's not to the scale here. At t equals 1, it's going to be 3, right? So we're going to have an impulse function times this much of amplitude, which is going to be 3 times 1 times delta of t minus 1. So it seems that a delta function, when it is multiplied by a function of time, or a function of whatever variable you've got here, time, frequency, whatever, does a kind of sampling. It samples the other function at the place of its existence, wherever it is. Now, we've got we have to calculate the multiplication of the input function, input signal, and the transfer function. So the product of delta function at 10k and h of f is calculated by replacing f where 10k with where that delta function is located, right? So this is the first term. So we calculate how much h of f would be at f equals 10k. Just replace f by 10k. We're going to have 1 over 1 plus j. And that is the value of the transfer function that needs to be multiplied by the same function, exactly the same as we have here. You don't get rid of the delta function. It exists. So this means that 1 over 1 plus j is the value of h of f at f equals 10k. And this term, 1 over 1 minus j, is h of f at f equals minus 10k. That is where the second delta function is located, and that samples the transfer function at f equals. Other questions? Part C of the same question is again a sine function, but it's a little different. The amplitude is still 1 millivolt. The frequency is now 100 kilohertz rather than 10 kilohertz. And we've got a constant phase of pi over 8. So going with the approach I suggested here, part C. the frequency of the signal, of the input signal, is now 100 k. You may calculate h of f, the magnitude, at f equals 100k. And the phase, again, at the same frequency. If this is the function, then how do we calculate the magnitude of the function? If this is a complex function, which evidently it is. What was the magnitude of a fractional complex number? 1 over square root of a squared plus b squared, right? So simply, the magnitude of the transfer function would be 1 over square root of 1 plus f squared over nk squared. The only variable is the frequency, which is going to be replaced with 100 kilohertz. And the same for the phase, which is the tangent of minus the tangent of f over 10k over 1. So let me see if I have the values for you to check. So it's going to be 1 over square root of 101, which is almost 0.1, the magnitude. And the phase would be approximately negative 0.47 pi. So what would be the output? The output,
So it goes tan inverse of real over imaginary over real, right? Right, the phase.
tangent of you've got a negative sign minus tangent of f over 10k over 1, right? So now that we've got the magnitude and the phase of the transfer function at the signal frequency of 10k, the output would be the amplitude of the input, which is 1 millivolt, times the magnitude of the transfer function. So 0.1 times 1 millivolt is going to be the amplitude of the output times the sine function, sine of 2 pi, and the frequency now is 100k, 100 kilohertz, t, plus the input is indeed 2 pi 100 kilohertz plus pi over 8. This is the constant phase that the input signal originally had, and now the contribution of the transfer function phase, which is minus 0.47 pi. So this would be the output.
So the generic one, just to repeat, would be the amplitude of the input times the amplitude of h of f. And then inside the sine or cosine, it would be whatever was there normally before the phase shift that we had. Just
Yes.
plug and match that. Okay.
assuming that the input is a single frequency sine wave or cosine. What happens if the input is a combination, a linear combination of two sine waves? Because of the linearity of the system, we find the outputs to each one of the inputs and then add them up. Or a linear combination, whatever combination you've got at the input. For instance, alpha x1 plus x2. If that is the input, then the output would be alpha y1 plus y2. Part D is a little different from A, B, and C. That is indeed a white Gaussian noise with zero mean value and RMS value of 1 millivolt. Do you remember what was the output of a filter or a linear system, whatever, when the input is a random signal or noise? We do have the transfer function.
Sorry, the input is always
The input is, yes, it is a random signal. How would you mathematically express a random signal? Do we have x of t, for instance?
Could we just assume it's impulse is like every frequency?
No.
It's an impulse, it's a transfer function, you know?
The randomness of the signal doesn't allow us to come up with a clear and certain expression, mathematical expression for the instantaneous values of the signal. So what we have for noise is PSD, power spectral density. G sub x of f, for instance, power spectral density of the input. So for the white noise, you remember what was the shape of the PSD?
For white noise.
For white noise. What was PSD? It was a constant value, right? And that would be n node over 2 because of the bilateral spectrum we're providing here, or spectral density. And what was n node? That was the RMS value, right? How much there? 1 millivolt. So this is the PSD of the input. And since the input is a random signal, even though the transfer function is deterministic and clearly defined, but since the input is of some uncertainty, the output would be also a random signal. So the expression we have to come up with for the output would be of PSD value. Okay. So if we have the PSD of the input, gx of f, and we have the transfer function h of f, what would be the PSD of the output?
That's a zero frequency.
This is not correct. I'm just putting h of f here to mention that the transfer function has a role. What was that? Say it again. transfer function squared
Oh, yes,
for PSD. PSD is of power type, for which we use the signal squared. So a squared version of the signal, a squared version of the other signal at the input and output, and then the transfer function appears here in the squared form. So we have to find the magnitude of the transfer function. What is the magnitude of this transfer function? 1 over
F over 10k all squared.
f squared over 10k squared. So h of f magnitude squared is this. Gx of f equals 1 millivolt over 2.
Sir, so you're getting rid of the J by square? Is that what you're doing?
No. See, these two lines denote the magnitude of a complex number, complex function, whatever. So the relationship we've got for the PSD of the output of a random signal is the PSD of the input times the magnitude of the transfer function squared. The magnitude of a complex number doesn't include the j. So it's 1 over the real part squared plus the imaginary part squared without the j. So this is where we get rid of j. And the squaring we've got here helps getting rid of the square root. So we've got 1 over 1 plus f squared over 10k squared. Now it is, well, the only thing that I have to apologize for is this is PSD, so 1 millivolt squared. 1 millivolt squared.
But why is it over 8?
And not over 2.
Well, this is just a notation. In our text, the explanation is this. It says, since this PSD is extended from negative infinity in the frequency domain all the way to positive infinity, but what we have in the real world is just frequencies from 0 all the way to positive infinity. So what we come up with as the power, or any form of power for the noise, is indeed representing just half of the spectrum. If you would like to draw a line that goes to the other half, so you're adding up another sectional area here that would not be present in the real condition. So if you would like to have a continuous line covering the whole frequency range, then you have to divide that value you come up with at the real condition from 0 to f, whatever large it is, divided by 2.
In that case, I have another question. So for part A of this, it's just a constant 1 millivolts times the unit step function. So would we be able to say, because we only consider real frequencies, that u of t, we just ignore it, and we just treat it as the constant 1 millivolts? Because every real system is a causal system. We can't have t less than 0. So for part A of the question, can we just say the 1 millivolts times the unit step is just 1 millivolt, and just focus from there on?
Any idea? The question was clear. Well, no, we're not allowed to do so.
Why are we doing it?
see, what is the meaning of a step function? There's a before and after involved, right? A step function indeed represents a stepwise change. That is the main information a step function tries to convey. So a sudden change. And the response of a system to such a signal would involve some transients that are associated with this step function. Right? So the Fourier transform of a step function usually brings terms into calculations, into the analysis that give us some transient behavior at the output. For instance, suppose that this u of t is the input. We have to come up with a better term. U of t is so suppose that we've got a first order filter or system. The output we expect is something like this, right? So being a step function rather than a constant one brings the study of this transient behavior of the output into existence. Otherwise, if we consider just the constant portion of the step function, the response to that constant value would be a constant value. So once a change occurs at the input, then some transient regime is observed. That is mostly because of the dynamic of the system. If the system is a first order one, then the dynamic gives us such a shape. If it is a second order system, then we would have some oscillatory transient regime. So it depends. Some other times you might have some changes, and in the end, in the steady state, the output would be 0. So this third one is the kind of response you will never see if there's no step excitation in the input. Stepwise change, whether it is a step function or an impulse function, so this is the difference. Find the autocorrelation function of x of t equals a cosine of 2 pi f naught t plus phi in terms of its period t naught. Find the average normalized power of x of t using p sub x equals r of 0. R denotes the autocorrelation function. Doesn't look familiar? So we are to find the autocorrelation 1 over T naught from negative T naught over 2, T naught over 2. Then we've got A cosine of 2 pi f naught T plus phi times A cosine of 2 pi f naught T plus phi plus tau. dt.
Sir, wouldn't it be 2 pi f naught then t plus tau in brackets?
Say it again.
Wouldn't it be 2 pi f naught then t plus tau together?
This way.
No, yeah, with phi being tau. Because technically t is there, isn't it? So
What?
what I mean is this. So when you have your 2 pi t plus tau, wouldn't it be like t plus tau over here and not just tau in the end?
Yes. You're right. 2 pi f naught tau. Okay. The variable t is now shifted by some amount, which is named tau. So what do we do now? There should be an identity for everything. A squared so let's first come up with something for this cosine of let's say alpha times cosine of beta. So what do we do now? What do we
1/2 cosine alpha minus alpha plus beta. Cosine
alpha
plus beta. Minus beta plus beta is the same in this case. Alpha minus beta. And then plus cosine of alpha plus beta.
Okay. So what makes it easy for us is that there are at least 2 terms that can be cancelled out if we do
Yeah.
this subtraction. So let's bring the 2 outside of the integral. Then we've got cosine of so what is the difference now? It's 2 pi not tau. Then we've got cosine of 4 pi if not t plus 2 pi
Plus our tau term.
plus the tau term. 2 pi if not dt, sorry, dt. All right. Now what?
So we can ignore the tau term and the phi term.
So this one is a periodic signal, periodic function. What is the cycle? What is it? No, the period can't be of frequency type. The frequency is twice as much as the original signal.
Half as much.
It's going to be 1 over 2. Right? So if we're taking the integral of this second term over a single period of the original signal, means that the integral is being taken on this second term over 2 cycles. So what is the integral of a cosine function over the course of a single integral? 0.
0.
A cosine function. What would be the integral over 2 cycles?
Yeah, 0.
Again, 0. So this term would go away. So what do you think? Now, what remains is the integral of this term times dt over the course of a period.
Sorry. What do you, the second term, the first part equals 0, but we still have the tau term. We can't just make the whole thing go to 0, can we?
You mean this part?
Yeah, I mean, like you said, this whole thing goes to 0, but we still have the tau term. How can we just say that it's equal to 0?
You admit that the integral of the summation of two terms would be the summation of the two integrals. Right?
Yes.
So this one goes away, but we still have this one.
No, I'm saying, how do you make that one go away?
This one because of this term.
Yeah.
Do you see anything time
Oh, it's
dependent? This is a constant phase,
Yeah.
right? It's again like a constant phase we already talked about. So what remains is this term. What is the integral of this term dt?
It's just that term.
Well, this is a constant value, constant in time,
Yeah.
right? So we've got this one times t from negative t naught over t to t naught. So we're going to have a squared over 2 cosine of 2 pi f naught tau. See, supposing that tau is not a function of time, it's and the fabric of tau is time, but it is not t. Let's say 1 second, 2 seconds, a constant value. It doesn't vary with time. So 2 pi times, let's say 1 kilohertz times 1 second would be a constant value. And cosine of a constant value, you can look it up on cosine table or calculator. So this would be a constant value, for instance, 0.85. So that constant value comes out of the integral, and what remains is just a 1 dt. This is not a function. If it was cosine of 2 pi f naught t, then had to be turned into.
We got rid of the t in the first line, basically.
We got rid of, actually we converted this product of two cosine functions into the summation of two cosine functions to be easier for the calculation of the integral. Then, fortunately enough, this is a periodic signal. The integral, and the cosine function will give us a 0 over, for the integral over an integer number of cycles, so this is 0, and this is a constant value. Now, this is the autocorrelation function, and what would be the power of the signal?
This is the autocorrelation at 0.
So what is the cosine of 0? It's going to be 1. And the end result would be a squared over 2. What we already know. purpose of this question was twofold, I guess. One is to do some practice for the calculation of the integral. And the second one is to see what is the effect of a constant phase shift. It doesn't change anything. The power of a cosine function of the amplitude of A would be A squared over 2 no matter how much the phase shift would be. Other
So do you have questions from your own prepared similar?
Yes, I do. The ones that you don't have an answer for. Did you calculate the RMS value of those sawtooth and triangular wave shapes?
So for the midterm, is it chapter 1, 2? Or
Chapter 1.
Chapter 1, right?
The whole chapter 1. Was there any problem, any difficulty?
So you said you're going to upload solutions to the whole second part, right? That's stuff.
This one.
You said you're going to upload solutions to this problem set, right?
Yes, actually, I do have the solution. I will post them on Google.
Yeah, I don't know where to be. Agreeing with, I don't know where to be.
Any question regarding the ensemble average, time average? Well, the ensemble average was something pretty easy, just for records. Suppose that x1 is this, x2 is this, x3 is this. The ensemble average is over any instant of time, for instance. This would be the ensemble average. And averaging over time for a single variable would give time average. Do we have any difficulty with the calculation of the autocorrelation function?
Go over a few examples.
Suppose that this is our signal, x of t.
Periodic.
in order for the two versions of the signal to be non-overlapping, tau would need to be greater than 2. That way, two signals would be non-overlapping, and the other correlation would be 0. Then let's move the shifted signal forward. When would be when the two signals start to overlap? That is for tau smaller than 2, greater than 1. For this case, this is 1, 2, 3, 2, negative 2, x of t. And now we've got some overlap. So, I'm sorry, I have to correct this. This edge would be shifted by tau. So this edge is the start of this complex. We go to the start of the other complex. Now, here's tau. Where is this point in terms of tau? This one's the shifted version of the end of the complex. So this would be 3 minus tau. Okay. So the overlap would be from 1 to 3 minus tau. From 1 to 3 minus tau. What is the height? 2 times, I'm sorry, this is a negative pulse. Please correct me before I go too much. So from 1 to 3 minus tau, we've got a negative pulse. Negative 4. And we are to calculate the area under the curve when we write that integral. Without bothering with doing the math for the integral, the area of this would be minus 4 times 1 times 3 minus tau minus 1. So 2 minus tau times minus 4. Whatever. Let me write it. 4 tau minus 8, right? This is the function. Yeah. 4 tau minus 8. line goes on and on until this edge gets to this point, right? So that is a delay of 1 second. So from 1 down to 0. This point would be 3 minus tau. Where is this one? What is that? This one is the edge at 2 that is now shifted by tau. So 2 minus tau. Product is now this overlap so from 1 to 2 minus tau. We've got a positive pulse. The height is 4. Then, from 2 minus tau to 2, we've got the product of a positive 2 and a negative 2. It's going to be negative 4.
So construct the integrals here from any of that.
Construct what?
Could you just go over this whole part again? So you got,
See, this is where the original signal is 0.
yes,
Right? So the product of 0 and a positive value would be 0.
yes,
This is 0.
yes.
Then we've got the overlap of the two signals, right? So this one, during this part, both are positive 2.
Like, how did you get 2 minus tau is my question.
Oh, this one?
Yeah.
This is the edge.
Indeed, yeah.
You know, the edge in the middle. And this one's the edge in the middle for the original signal. So everything is shifted by tau. So I just find where the original version of this edge is, which is at 2. Now it is shifted by tau, so this would be 2 minus tau.
And how do you get 3 minus tau there again? 3 minus tau is because 3 is the final one.
So this one is the final one, and this one is the final one. 3 minus tau.
Oh, then
So
makes sense.
from 2 minus tau to 2, we've got the overlap of a positive and a negative level. So here we've got negative 4. Then again, this one's another overlap, both pulses are negative, so the product would be positive. Of the same height of 4. Then from this point on, the shifted signal is now 0. Even though the original signal is not 0, the product would be 0. So where's this one? This is 2. How about this one? This edge is at 3, negative 12. We are after the integral of this product from negative infinity to positive infinity, meaning that we are after the total area, the algebraic summation of the positive and negative areas. So these three. Just remember that these are positive and this one's negative. So the other correlation would be 4 times 2 minus tau minus 1. That's the first one. Minus 4 times 2 minus 2 minus tau plus 4 times 3 minus tau minus 2. So what is that going to be? So that one gives us 4. Then these two are cancelled out. Here we've got another 4. Then here we've got minus 4 tau, minus 8 tau, minus. So, please double check to make sure that I didn't make a mistake. And we know that for negative taus, the exact results would be achieved because of the symmetry of the correlation function. So beyond 2, the function is 0. Between 1 and 2, we've got 4 tau minus 8, meaning that at tau equals 2, we've got 0. At 1, we've got negative 4. Then between 0 and 1, this is the relationship, 8 minus 14. So for tau equals 1, we've got something wrong here, please double check, because this was just something I threw out here on the board, not something I already prepared for you. So at 0 we've got 8. Please double check to make sure that I didn't make any mistake. Should be something wrong here. So that's 4.
It looks right.
Which one? This one? So that is minus 4 tau. Here's another minus 4 tau, which is minus 8 tau.
Plus 4 tau, or minus.
Minus 12 tau. Is that right?
Yes.
Minus 12.
That's right.
So if that is, okay, so for tau equals 1, we've got negative 4. And then we come up with 8. Something like this. Believe me, it's not that easy to write, to draw a straight line on the board without any tool. But it should be something like that.
I think it's pretty safe to say that we're going to get one of these kind of questions in the midterm. There's like a billion examples in the class.
Well, yes, actually. This means that it is important. All right. Sorry, I don't have any more time left. I have to leave. I wish you an easy exam.
Well, that's up to you, sir. That's up to you, not us.
No, actually, unfortunately, I don't agree with you. You know, the difficulty of a question, a problem, an exam is not the exam itself. It is, at least partially, it is your preparation that makes a problem easy or difficult. So I hope you get prepared more and more. We still have a couple of days, right?
Yeah.